Hi, this video we're gonna continue look at using the STEM table, and through this example the goal is to apply linear interpolation to solve some unknown property. Okay, so here we just focus on C because we did question A and B in the previous video. So in this problem, it's given two properties. The first one is pressure 1000 kilopascal, and give us the internal energy, specific internal energy 2950 kilojoule per kilogram. Then we need to find the temperature and quality and phase. Okay, so giving us pressure, giving us internal energy, we have no idea what phase this is. So that's going to be our first mission, to find out what phase it is. And then since we know the pressure, then immediately we know we're going to use table A5, the pressure table. And once we're in the pressure table, how do we determine what phase it is? We're going to find our UF and UG, and then we're going to look at this given U. How is that compared to UF and UG? Like we said, if U is greater than UG, that's going to be superheated vapor, right? And if it's U is between UF and UG, we know it's a mixture. It's a saturated liquid vapor mixture. And if U is less than UF, we know that's going to be a compressed liquid. So that's going to be our guideline. And in order to do that, we have to find those two numbers, UF and UG, from the table first. So let's go to table A5 and look at 1000 kilopascal. So I encourage you to do the same thing using your table. Like I said, being able to look up those numbers in the table, it's a necessity for thermal. Okay, so 1000 kilopascal right here, and we are looking at UF and UG. So UF is a 76139. And now let's go back to look at the UG. UG is 2582.8. Okay, then we realize our U here is 2950, and it's even greater than UG. That tells us this is superheated vapor. Okay. If it's superheated vapor, the quality is not available, right? Why? Because quality only applies to saturated liquid vapor mix. There's no quality anymore if it's a superheated vapor, because there's no saturated liquid or saturated vapor. It's now superheated vapor. Again, quality only applies to the mixture. Okay, now the only thing left is to help us to find out the temperature. Well, now we know it's a superheated vapor. Table A5 just facilitate us to figure out what phase it is. Now we know exactly it is in superheated vapor. Now we're going to go to the right table. So what do you think? Which table? Table A6, right? Table A6 is superheated vapor. And now in the previous STEAM table basics, we're talking about for table A6, superheated vapor, there are many tables. It's categorized by pressure, and our pressure here is 1000 kilopascal. 1000 kilopascal is how many megapascal? It's going to be 1 megapascal. So we're going to look at 1 megapascal, and the second property we're given is, remember, is U, right? It's specific internal energy as 2950. So we're going to go to that table, 1 megapascal. See if we have luck finding 2950 in this U term. Let's see. 2950, we're getting close. This is 2875, this is 2957. So it's between those two rows. It's between the temperature at 350 and 500 degrees Celsius. and that's in between of our 2950 internal energy. That's the point of this video. Using linear interpolation to figure out exact temperature. We know the temperature is between 350 to 400, but how much exactly? So here we go. In order to do that, for linear interpolation, first step is going to be write down those numbers. So I'm going to take a picture of this right here, and I'm going to get back here to see my U. I'm gonna write down a table, so temperature column and a U column. Our temperature column, we said it's between 350 degrees Celsius and 400 degrees Celsius. And our U corresponding to 350, the U is 2875.7. 2875.7. And now let's go back to look at 400 degrees Celsius. Our U is 2957.9. Why do we use those two numbers? Because your U here is between those numbers, right? Okay. Our U is 29570, 2950, and we need to find the corresponding T. So in order to do that, I will illustrate a linear interpolation concept. If we were using U and T for Y and X axis, for 350 and 400, at 350 we have 2875.7. At 400 we have 2957.9. So we have those 2 points. Here we go. And then this unknown temperature, this U we're calculating is somewhere here. That's 2950. And our goal is what? To finding corresponding temperature. This one right here. Okay? In order to do that, we're going to set up the equation. Linear equation, basically using the slope. The slope, quick review, is rise over run, delta y over delta x. So we're going to use this known point, right? Those 2 blue points. So our delta y, which is our U, delta U, 2957.9 minus 2875.7. That's our delta y, which is delta U here. And our delta x is going to be 400 minus 350. That's our slope. That's going to be equal to what you're solving, this one right here. And thus our internal energy is 2950. And you can either use this 0.1 or 0.2, but I'm just going to use 1. It doesn't matter, you're going to get the same results. If I use 1, I'm going to minus 2875.7. So that's going to be the delta y between those 2 points, right? And now we're going to figure out the delta x. So have to be corresponding. 2950 corresponding temperature question. That's what you're solving. And 2875.7 corresponding temperature 350. Here you go. Then you can solve this question mark. Or you can use the same thing to say, if I'm going to use 0.2, we can. So I'm going to just demonstrate to you. For that situation, you can go ahead and say, okay, we're going to use 2957.9. That's our U minus this U minus 2950. That's going to be the difference between those 2 points, right? And our delta X will be 400 corresponding to 957.9 minus question mark. So either this or that will give you, solve this, get the same answer. So I'm going to go try what do we get. So there are many ways to solve this. You can go ahead and solve this and then cross multiply. And so my final answer for this is 395.19 degree. Now let's take a moment to say if this number is reasonable. We know this number have to be between 350 and 400, right? Like the table you're taking it out. And 2950, it's more close to 2957.9 compared to 2875.7. So the temperature should be close to 400. Yeah, and our number is 395. So, okay, I said, okay, this number seems to be in a ballpark. And then we figure out the temperature. This is our T. All right. So this is example for linear interpolation, and also we venture into superheated table for this one. And that's all we got for this one. See you next time. Bye.